Okay, in this video, we are going to be looking at variation. Where's that word? Here we go, variation. So we're going to be looking specifically at direct variations and inverse variations, sort of know how to tell the difference between the two, and then also how to solve some problems down here, solve some problems that involve both of those variations. One thing that's important to note about direct and inverse variations or relationships is that they're very common. Here's just two quick examples. In chemistry, the concentration of a solution varies inversely as the volume. In other words, the greater the volume, the less the concentration. Here's another one. Ohm's law says that voltage varies directly as the current. Or in other words, as the current goes up, the voltage will go up, or vice versa. So, and we're looking at just these two direct and inverse variations, but there's plenty of other types of variations. But in order to work with those variations, they'd be similar to what we'll do in this section. Okay, first let's start with direct variation. Here's an example of a graph of direct variation. Notice that the higher the intensity, the higher the voltage. So if one thing goes up, the other thing goes up. Notice also here on just this data table that if my voltage is 10, intensity is 5. If I jump my intensity up to 6, then this one goes up to 60. So see how there's a relationship between them, how each one goes up as the other one goes up. And that is known as direct variation. Now, how about, there's got to be some kind of a pattern between those. Like I see that this one goes up, but this one goes up, but is there an amount that it goes up for every one of these? Like it seems like this one goes up 1 for every 10 that those goes up. So 8 here, if that goes up by 1, it looks like this one goes up by 10 as well. So there's some kind of pattern. So mathematically, we can identify that pattern just using a few little tricks. That pattern that we're looking at in terms of variation is called the constant of variation. Here's how you do it. So if they say voltage varies directly as the current, you would put V, and this symbol here means varies. So this varies, and directly means it's on top here as the intensity. Now from that, we can write, sorry for my cough, we can write, so it varies as the intensity, but there's got to be some kind of constant of variation. So I can write a formula. Voltage is equal to some constant multiplied by intensity. Now, if I take a look at my data, I can plug some numbers in here and determine what that constant of variation is. So let's try. Let's say pick this one. So if the voltage is 70 is equal to constant I don't know multiplied by the intensity is 7. So now to solve for k, I'll divide both sides by 7. Divide this side by 7. So my constant of variation is 70 divided by 7, or 10. So if they were to ask me another question on that, say they wanted to know what the voltage was when the intensity was, say, 15, for example. You might be able to figure that already. But I could use my formula, because my formula now is voltage is equal to a constant, which I now know is 10, multiplied by the intensity. So if they tell me that my intensity is 15, I can plug that right where the I is and multiply, and I'll get my voltage to be 150 volts. That's what my voltage would be with an intensity of 15. You get the idea? So it's almost like a two-step thing, where first you figure out what the constant is, and then second you use that constant to help you solve another question. I'll do a couple of examples like that. So here they say y varies directly as x. So y varies directly as x. So I put an x right there. And right from that relationship there, I can change it so it's y is equal to some constant multiplied by x. So initially they tell me that y is 16, 16 equals, k I don't know, when x is equal to 8. I put an 8 here. To solve for k now, you're probably thinking just divide by 8, that's right. 16 divided by 2, or by 8 would be 2. So my constant of variation is 2. Now I can rewrite this formula right here, putting a 2 in for right there. So for that particular variation, y is equal to 2 multiplied by x. So then they say, determine what y is when x is 16. Okay, I can do that. Y is equal to 2 times, they said x is 16, I put a 16 there. So when x is 16, y turns out to be 32. Again, 2 steps. First, figure out the constant. Second, use the constant in figuring out whatever question is asked. Maybe try this one. Press pause, try it, and then press play and see if you're on the right track. Y varies directly as x. So y is equal to some constant multiplied by x. Y is 21. When x is 3, divide both sides by 3, I get a constant is equal to 7. Then they say find x when y is 42. So my equation is y is equal to 7 times x. They say plug in a 42 for y is equal to 7 times x, and they want us to find x. I'll divide both sides by 7, so I'll get x is equal to 6. Okay, so that is direct variation. Now here's an example of a graph where we're looking at inverse variation. Notice that as this one goes down, this one goes up. Or if I look at the table, this is concentration. So as the concentration goes down, it looks like the volume is going up, or vice versa. So if they're going in opposite directions like this, it could be an inverse variation. So when one is divided by 2, the other is multiplied by 2, if there's that consistency there, then we have inverse variation. Let's try a question where we look at that. So number of hours it takes for a block to ice melt varies inversely as the temperature. So hours varies inversely as the temperature. So I have to, instead of putting a t here, that'd be direct, I have to go 1 over t, inverse variation. Okay, so I can write an equation from that. H is equal to some constant divided by t. And then I'll do the same thing as I did before. 2 hours to melt at 35. So the hours is 2 equals K, the temperature is 35. So solving this equation, instead of dividing this time, I have to multiply both sides by 35. So I get a constant is equal to 35 times 2, or 70. So now my equation I can rewrite as hours is equal to the constant, which is 70, divided by the time. Now let's look to see if they have another question. Find how long it will take, so I'm looking for time, if the temperature is at 20. So that's how hot it is. Am I getting my H's and T's mixed up? Hours. What did I do there for hours? Oh, I was right. So how long, that would be hours. And here would be my temperature. So let me go back down. Temperature is 20. So here in my equation, temperature is 20. H is equal to 70 divided by 20. And when you divide those, you get, I think, 3.5. So it would take 3.5 hours if the temperature is 20. Let's just look back and see if that makes sense. So if the temperature is 35, it takes 2 hours to melt a block. So if I lower the temperature, it makes sense that it would take longer in order for that block of ice to melt. Okay, let's try 1 or 2 more. And feel free to pause and try these on your own. Force needed to break inversely with the length. Varies inversely as the length. Okay, so force is equal to some constant divided by the length. Now let's see what information they give us. 5 kilograms of pressure. That's probably should, in terms of force, we probably should have those in newtons. Or whatever, we'll just use the 5 for now. So the force is 5 is equal to some constant divided by the length is 2. So to solve for K, I'll multiply both sides by 2, and I get a constant to be 10. Therefore, my equation, this one here, for this specific example, is force is equal to the constant is 10 divided by L. So now this is a relationship specifically for this particular board. And it'd have to be a different kind of board, or specific kind of board. Now they say how many kilograms of pressure, that's F, so F I don't know, will it take to break a board that's 6 feet long. So if it's way longer, you would think it would take less pressure if it's inverse. Let's see. So it'd be 10 divided by 6. Okay, 10 divided by 6 is about 5/3. And if you divide those, that's about 1.67 approximately. So when you take a look at it, the longer the board this time is 6, then it takes less pressure. In this case, the board was only 5 and it took more pressure. More pressure. Try one last one. Again, pause, try this one, and then come back. Speed varies inversely to time. So 1 over time. Or speed is equal to some constant divided by time. A biker traveling 30 kilometers an hour, so that's 30, is able to cover a distance in 1.5 hours. So K over 1.5 hours. Multiplying both sides by 1.5, and you get, whoops, that's K, is equal to 30 times 1.5, I think is 45. So my constant's 45. So I can rewrite this formula here as S is equal to, my constant I now know for this specific example is 45 over T. Then they say, if you slow down to 20, how long will it take to cover the same distance? Well, if you slow down, it's got to be more time, right? Let's see if that works out. So the biker slows to 20. So speed is 20 now, is equal to 45 over T. Here my equation, the T's on the bottom, so I'll need to multiply both sides by T. So on this side, I'll get T times 20 is equal to, the T's cancel out, it would be 45. And then divide both sides by 20, so I get 45 divided by 20, which I'm not sure what that is, 2.25 or something. 5 goes into that 9, 5 goes into that 4. So yeah, so 2.25 hours. So in the first case, it took 1.5 hours to cover it. And now if I'm going slower, it's taking more time to cover that same distance. Okay, so it makes sense, that inverse proportion. So in this video, we have looked at variation. We've looked at direct variation, and we've looked at inverse variation. And I've shown you 4 or 5 examples where you use 2 steps. First, find K, and then in the second, use K to solve the next question. Hopefully that helps. Try some questions.